this is Lab 4 Part 1 Stepper Motor Controller. So we are required to develop a more step machine that will provide the sequence of the signals based on the three inputs EN, CW and clock. So this is the stepping sequence. If the CW is 1, the sequence will go clockwise S0 to S1 to S2 to S3. So if the CW is 0, it will go anti-clockwise from S3 to S2 to 1 to S0. So the EN here, if it's 0, the output of the motor remains fixed. That means the present state and the next state is the same. So when EN is 1, the output will change accordingly based on the CW input, either in clockwise or anti-clockwise. So the clock is to control the speed of the stepping motor. So with all this information, you can create the state diagram. So this is the state diagram of the Mo step machine. So this is the legends. So you can see the input is here, EN and CW. So from this table, we can determine the next state of the step sequence. So if the EN is 0, like I mentioned it before, the next state will stay the same as the present state regardless of the input of the CW. So S1 stay the same, S2 same, S3 same if the EN is 0. So when the EN is 1, the next state will change according to the input of the CW. So when the CW is 0, the next stage will go to S3, which is anti-clockwise. So when CW is 1, the S0 will go to S1, which is clockwise. The same goes to S1, S2 and S3. So the output here is based on the diagram here. S0 is 1 0 0 0, S1 is 0 0 1 0. So 1 0 0 0 0 0 1 0. Same goes to the S2 and S3. So with all the information here, we can complete the truth table. So after we complete the truth table, we can get the equation of the J, K, JB and KB. So we can create the schematic and the circuit connection. So this is the output. So this will be our schematic diagram, and this is the circuit connections. So for this one, we use one JK flip-flop, one 2 input NAND gate, one 3 input NAND gate, and one NOR gate. So now we move to the hardware part. So as you can see now, this is the EN, this is CW, and this is clock. So when EN is 0, the stepper motor stay the same. That means the present state and the next state are the same. Nothing happened. So when EN is 1, the direction will change according to the CW. So in this case, CW is 0. So this means it goes anti-clockwise. So let's speed up first. So when CW is 0, the direction go to anti-clockwise. So when CW is 1, direction will goes to clockwise. Thank you.
Okay, this is part 2 of our lab 4 for DED Lab. So for this part, we have to construct this circuit by using a shift register instead of individual D flip-flops. So let's look at the first question. It says, what is the use of this gate, this XOR gate, in this whole circuit? So So in case, let's assume that the values of the states are initially 0, 0, and 0. So if that's the case, according to this state diagram, it will get stuck at 0, 0, 0 forever. So if we connect this part, which is supposed to be ground, to a switch, so in case it starts at 0, 0, 0, we can press the switch and make it VCC instead. It will escape the loop of 0, 0, 0 and move on to 0, 0, 1. So by doing this, it will escape 0, 0, 0. So then it will move on to the rest of the loop without going back to 0, 0, 0 again. So uh, so we constructed this circuit using the shift register. You can look at here, and this is the schematic. This is the schematic of the 3-bit left linear feedback shift register. So the reason we connected X1, which is in this diagram, to Q1 here is because, as you can see, the input here feeds the input here feeds the input of Q0. Q0, which is the first flip-flop here. This is the input. So moving on to the second input, it's X1. So for the second input here, it's Q1. So X1 is connected to Q1. And moving on to the third input, to the third D flip-flop, it's X0. So X0 is connected to the third D flip-flop here. So that's how we figured out which leg is connected to which pin. So after that, we follow the same, the same connection for the XOR gates. And we got the values here as stated in the oscilloscope. And let's have a look at the diagram here. So supposedly it's supposed to go from, according to this state diagram that we constructed, it's supposed to go from 1, 0, 0 to 0, 1, 0 and moving on. And with XO as the first bit, according to our assumption. So as we connected the XO to the, the oscilloscope, we can observe the behavior of XO compared to the clock. So as you can see here, let's start here. So this is one clock cycle, and XO is 1. So we'll be starting here, 1. The first bit is 1. After that, we move on to 0. So for the next clock cycle, it goes down to 0. And after that, it will have to go through 3 ones, 1, 1, and 1. So it continues for 3 clock cycles, 1, 1, and 1. And after that, it will have to go to 0 and then another 0. So there are 2 zeros here for 2 clock cycles. Then lastly, it will go back to 1, 0, 0 again. It will go up here and repeat the cycle all over again. So yeah, the sequence here does appear to be pseudo-random. So that's all for this part, but we'll continue on with the 7-bit linear feedback shift register. Okay, so now this is the second part of part 2 of Lab 4. And in this part, we are supposed to construct a 7-bit LFSR from our previous 3-bit LFSR. And it's written here, we only have to move 2 wires, and that's actually the case. So for this is our 3-bit one. So we move the input for this XOR gate from 4 and 5 to 6 and 12. This is because it's written here, the output X7 equals to X3 XOR X0. So X7 is here, similar to the 3-bit LFSR. This the input being fed into the shift register is X3. Then we go on X2, X1, and X0. So similarly, this is X7, and we go X6, X5, X4. This is X3, X2, X1, and this is X0. So that's how we do it. And now you can have a look at the circuit here. It's been constructed. And according to the digital oscilloscope, there's a pseudo-random sequence of numbers. So let's say it's 1 for 2 cycles and 0 for 2 cycles, 1 for 2 cycles again, 0 for 1 cycle, and 1, 1, 1 for 2 cycles, 1 for 2 or 3 cycles, and therefore you can have a look at that, and it's actually quite random as compared to the the clock is consistent, and over here is the output, which is quite random. And yeah, that's all for this part. Thank you.
Now I am doing Lab 4 part 2. Now we are going to design a mini step machine to detect the sequence 0, 1, 1. And this is our mini step machine, and this is our output. Okay. Now we are going to using the part 2 S0 to be our part 3 input, and it's linked to this side. This is a NAND gate. We're using De Morgan to change it to NAND gate, and this one is no gate. We also using De Morgan to change it. Okay, and this is our part. When W is equal to 0, he will come to the F0 step. When the next step, when he become 1, he will come to the 0, 1 step, and he will become 1, and he will count out the output equal to 1, and this is our answer. Now we are going to see the oscilloscope. In the diagram we can see when he equal to 0, 1, 1, our output will be 1, and this side also when the input is equal to 0, 1, 1, the output will be 1. That's all.